Myself, Madhuri Modak, Assistant Professor in Mathematics, Department of Computer Science, Avedai Namdar Senior College. Now, in the paper Groups and Coding Theory, we have seen first and second unit. Now, first unit was introduction. In second unit, we have seen definition of group and some examples of finite and infinite groups. Now, we start with the third unit, that is finite groups and subgroups. Now, the last part is cosets. Definition, examples, and properties. Let G be a group and H be a subgroup of G. Then the set HA, which contains H into A, H in H, is called as the right coset of H in G. Also the set AH, which is A into H in H is called as the left coset of H in G. So here the element A in G is fixed. For that element we are finding right coset, as here A is written to the right of H, and this is left coset because A is written to the left of H. Now one example, let G equal to Z6 and H is equal to 0 bar 3 bar is a subgroup of G. Now we have to find all left and right cosets of H in G. Now Z6 is a group with respect to addition. So for A belonging to G, left coset of H in G is written as A plus H. Now why we are writing plus here? Because Z6 is a group with respect to addition. So for every element A in G, we find the sets of the type A plus H, and all these are considered as left cosets. So A plus H is A plus H, where H is in H. It means we are adding A in every element of H from the left hand side. Similarly, right coset of H in G is written as H plus A, which is H plus A, H in H. So we are adding A in every element of H from right side. Now we find left cosets of H in G. Now the first element of G equal to Z6 is 0 bar. So what is the left coset of 0 bar? 0 bar plus H. So add 0 bar in every element of H. The elements of H are 0 bar, 3 bar. So add 0 bar from left side. So it is 0 bar plus 0 bar, 0 bar plus 3 bar, which is 0 bar, 3 bar, H itself. For A is equal to 1 bar. Left coset 1 bar plus H. It is 1 bar plus 0 bar, 1 bar plus 3 bar. So we are adding 1 bar in each element from left side. So it is 1 bar, 4 bar. Now for A equal to 2 bar, similar way it is 2 bar, 5 bar. Similarly for 3 bar, 4 bar, 5 bar. So for 3 bar we are getting the same set H. For 4 bar we are getting 1 bar plus H. And for 5 bar we are getting 2 bar, 5 bar, which is same as 2 bar plus H. So these are the left cosets of H in G. So actually there are only three distinct or different left cosets, namely H, 1 bar plus H and 2 bar plus H. Similarly, we can find the right cosets of H in G. So here in every element of H, we are adding that fixed element A from the right side. So for A is equal to 0 bar, right coset H plus 0 bar is equal to 0 bar plus 0 bar, 3 bar plus 0 bar, which is 0 bar, 3 bar equal to H itself. Then A equal to 1 bar. So H plus 1 bar is 0 bar plus 1 bar, 3 bar plus 1 bar, which is 1 bar, 4 bar. Same way for A is equal to 2 bar, adding 2 bar in every element of H from right side, it is 2 bar, 5 bar. Again for 3 bar, 4 bar, 5 bar, we are getting H, H plus 1 bar, H plus 2 bar. So we have only three distinct or different right cosets, namely H, H plus 1 bar and H plus 2 bar. Now remark, if G is abelian, then for any subgroup H of G, H equal to HA for all A belonging to G. That means if G is abelian group, then commutative property holds, and hence left coset of H in G is same as right coset of H in G. Now similar to example 1, here for G is equal to Z plus and H is equal to 3Z, we can find left and right cosets of H in G, which you can try at home. Now these are properties of cosets. Let H be a subgroup of G and A and B are elements of G. Then A belongs to AH. That means the element A is present in the left coset AH. Then AH equal to H if and only if A is an element of H. Third, AH equal to BH, that means these two left cosets are equal if and only if A is an element of BH. Then fourth is very important, AH equal to BH or AH intersection BH is phi, that is any two left cosets of H in G are either identical, means they are exactly same, or disjoint, means nothing is common. Now, let H be a subgroup of a group G, then AH equal to BH if and only if A inverse B is present in H. Second, order of H or cardinality of H is equal to cardinality of BH. That is, number of elements in any two left cosets of H in G are same. In previous case also we have found different cosets, their orders are same. Third, H equal to HA if and only if H is equal to AHA inverse. Next theorem, let H be a subgroup of G. A is an element of G, then H is a subgroup of G if and only if A is present in H. Now Lagrange's theorem, if H is a finite subgroup of a finite group G, then order of H divides G. That is, order of subgroup divides order of the group if the group is finite. Now, from this theorem, there are two corollaries. First, if G is a finite group and A is an element of G, then order of A divides order of G. That is, order of the element divides order of the group if the group is finite. Then second, a group of prime order is cyclic. So if you consider any group whose order is a prime number, then definitely that group is a cyclic group. For example, if we consider any group of order 11, then 11 is a prime number. So definitely that group is cyclic. State true or false with justification. A group of order 19 is cyclic. See the order of group. It is 19. So 19 is a prime number, means definitely by using corollary 2, that group is a cyclic group. So even though we don't know what is that group, just by checking the order of the group, we can say that it is a cyclic group. State true or false with justification. In a group of order 100, there is an element of order 34. Now we have seen that in a finite group, order of an element divides order of group. Here group has order 100, which is finite, and order of element is 34, but order of element must divide order of group, and 34 does not divide 100. So there does not exist an element of order 34 in a group of order 100. It means statement is false. State true or false with justification. There exists a subgroup of order 12 to a group of order 40. Again, by Lagrange's theorem, order of subgroup divides order of the group if the group is finite. Here order of group is 40, and if there exists a subgroup of order 12, then 12 must divide 40, but 12 does not divide 40, and hence the statement is false. Similarly, h a square is equal to h into a square, where h is an element of h. So multiply every element of h by a square from right side. So it is a square a raised to 7 a raised to 12. Similarly, we can find the remaining right cosets. So some of the right cosets are identical. So observing the identical right cosets, we get only 5 right cosets which are distinct. Now, as G is a cyclic group and every cyclic group is abelian, G is an abelian group. So, whatever are the right cosets we got, same are the left cosets, because in a abelian group, left cosets and right cosets are same. Thank you.